Hello and welcome to this video on finding the derivative. In this video, we look at how to generalize the method from the previous video to find a formula for the gradient function of a particular curve. To approximate the gradient on the curve y equals x squared when x is 5, we could just pick a point on the curve just slightly to the right and then find the gradient between the 2 points. As the second point gets closer and closer, the gradient becomes a better approximation of the true gradient. This is what we did in the previous video. So in the diagram on the left, using 6, the gradient of the chord is 11, whereas in the diagram on the right, using 5.01, the gradient of the chord is 10.01. The actual gradient when x is 5 is 10, so this approximation is very close. However, although this gives us a numerical method to get the gradient at a particular value of x, it doesn't give us the gradient function in general. So let's use exactly the same method, but this time we'll keep x general and make the small change equal to h. So in the diagram at the bottom left, we've got the curve y equals x squared. And if we start off with our points using x, y will be x squared. And if we add on this small change h, the x value will be x plus h and the y value will be the square of x plus h. So then looking at the top right, where we have our methods, we're saying that the gradient in the limit of h tending towards 0 is given by the change in y over the change in x. The change in y, in this case, is x plus h all squared minus x squared. The change in x is simply h because we've added h on. If we expand the brackets, the numerator becomes 2xh plus h squared, and we're dividing that by h. And then if we cancel through, we get the limit as h tends to 0 of 2x plus h. And as h tends to 0, that's going to equal 2x. So the h disappears as h tends towards 0, so we can effectively treat it as 0 at this point, which gives us the 2x we found in the previous video. This process is known as differentiating from first principles, and the gradient function or derivative of the curve y equals f of x is written as f dash x or dy by dx. So f dash x in the limit as h tends to 0 of the change in y over the change in x, where the change in y is f of x plus h minus f of x, and the change in x is h. The gradient function can be used to find the gradient of the curve for any value of x. Okay, we're going to need to look at a couple of worked examples. So we're going to start with a worked example from the textbook. The point A with coordinates 4, 16 lies on the curve with the equation y equals x squared. At point A, the curve has gradient g. Part A show that g is 8 plus h as h tends to 0, and part B deduce the value of g. So I've written out my solution. You can see I've numbered the lines of working down the side 1 to 6. So in line 1, I'm simply saying that 4, 16, as we add h to it, is going to go to 4 plus h and 4 plus h all squared. So in line 2, when I use the formula, I'm saying that g in the limit as h tends to 0, change in y over the change in x, f of 4 plus h minus f of 4 over 4 plus h minus 4. So f of 4 plus h is 4 plus h all squared. F of 4 is 16, so we're subtracting 16 from 4 plus h squared, and we're dividing by 4 plus h minus 4, which is h. In line 3, I'm expanding the brackets to get 16 plus 8h plus h squared minus 16 all over h. In line 4, the 16s have cancelled to give me 8h plus h squared over h. And in line 5, I'm dividing through by h to get the limit as h tends to 0 of 8 plus h, as requested in part A. For part B, in line 6, we're simply saying that as h tends to 0, 8 plus h, of course, is going to tend to the number 8, which is the value of g. So the value of g is equal to 8. But this is the worked example you really need to concentrate on. It's showing from first principles the derivative of a function is whatever it happens to be. In this case, it's taking x cubed and proving from first principles that the derivative is 3x squared. So in line 1, I am quoting the formula that we're using. So f dash x, the derivative, is equal to the limit as h tends to 0 of f of x plus h minus f of x over h. And that's the formula you're going to be using whenever you prove something from first principles. In line 2, I am substituting the actual function in this question. So the function is x cubed, so f of x is x cubed, and f of x plus h is the same as f of x, but replacing the x with x plus h. So rather than being x cubed, it's going to be x plus h all cubed. So line 2, the change in y, x plus h cubed minus x cubed, divided by the change in x, which is h, always. For line 3, I'm expanding the brackets. If you know the binomial expansion, then that's what I've used to expand the x plus h cubed. Otherwise, I'm simply doing x plus h times x plus h, and then whatever the answer is, I'm timesing that by x plus h. That gives me x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed, all divided again by h. A very common thing in this method is that when you go from lines 3 to 4, you've got the x cubed at the very beginning of the numerator and a negative x cubed at the very end of the numerator, or it might be x to the n and minus x to the n will cancel out. So line 4 is simply the same as line 3, except our x cubes have cancelled out to leave us with 3x squared h plus 3x h squared plus h cubed, all divided by h. And then in line 5, we're dividing through by h to get 3x squared plus 3xh plus h squared. And then in line 6, okay, we've been looking at the limit as h tends to 0 so far. So if we actually make h equal to 0, or h tends to 0, what we're going to be left with is simply 3x squared, which is the answer to the question. Thank you very much.